In the previous video, we discussed the half-wave rectifier with resistive load, and we found that this circuit gives you an output that looks like a half sinusoid. So half of the sinusoid will appear and then zero. Again, the positive half appears and then zero. And we also calculated many parameters. We calculated the peak inverse voltage. We calculated the maximum forward current. I can ask you here also to calculate the average of this sinusoidal or half sinusoidal wave with V output peak, which is equal to Vs peak minus VDO in case of constant voltage drop model. So here this sinusoidal wave, it appears only between, for half of the period, between let's say 0 and t over 2, while for the other half it's 0. So if I ask you to calculate the average, you can do that using the integration. So you can integrate over one period and then you divide over the period. So V output average equals 1 over the period. Integration over one period, V output of t dt. But V output, it exists only, or it appears only in half of the period. So the integration will be over half of the period. V output peak sine, let's say, omega t dt. And then if you do this integration, and I will leave this to you, you will find that V output average will be Vs peak minus VDO over pi. So Vs peak minus VDO over pi. And you can do that by yourself. Now let's ask a question. What happens if we replace the resistance here by a capacitor, like this circuit? So we replace the resistance by a capacitor. Let's look at this circuit. This circuit is called peak detector circuit, and we'll understand why they name it like this in a few minutes. Let's see how the capacitor will behave and what will be the output voltage across the capacitor. So now, for this circuit, if Vs changes like a sinusoidal wave, this is Vs with time, what will be the output? Let's assume ideal diode for simplicity. In the positive half cycle, the diode will be on, okay, and the capacitor, the voltage across the capacitor will be exactly equal to Vs. So in the beginning, when the input increases in the positive half cycle, the output voltage will increase exactly similar to Vs. So in the positive half cycle, the output will be the same as Vs. So the voltage across the capacitor is going to increase, the diode will be on, the voltage across the capacitor is going to increase exactly the same as Vs. But once Vs starts to decrease, so the capacitor will charge until it reaches Vs peak. Once Vs here starts to decrease, what happens? The capacitor is charged with a high voltage, and the voltage here in this side is going to decrease. So the capacitor will provide higher voltage than this side, and the diode will be off. So starting from this point, the voltage of the capacitor is Vs peak. This is the voltage of the capacitor, while the input Vs will start to decrease. What happens? The diode will be off. Starting from this point, the diode will be off. If the diode is off, there will be no current in the circuit, and the voltage of the capacitor will remain as it is, right? And then the input Vs decreases and then increases again and reaches here. Again, for the rest of the time, you will find that Vs, for the rest of the time, starting from this point and on, Vs will be less than the voltage of the capacitor, right? And hence the diode will be off, and the voltage of the capacitor V output will remain constant like this. What if the input was not sinusoid? What if the input was something else, changing voltage, some random voltage? What will happen? Let's see, to understand how the circuit works. If the input was something like this, let's assume something like this. The capacitor is going, in the beginning, when the input is positive, the capacitor is going to charge, and then starting from this point, the source voltage will be smaller than the capacitor voltage. When the source voltage is smaller than the capacitor voltage, the diode will be off, and the capacitor voltage remains as it is. Until the input, the source voltage increases more than the capacitor voltage. When the source voltage is higher than the capacitor voltage, the diode will be on again, and the capacitor will charge again, right? So once the Vs that I plot in white here, Vs, this is the source voltage, is higher than the capacitor voltage, the capacitor is going to charge again. The diode will be on, and the capacitor charges again, until we reach this point. Starting from this point, the source voltage will be lower than the capacitor voltage, so the diode will be off, and the voltage of the capacitor stays constant. Until, again, the source voltage increases above the capacitor voltage, then the capacitor is going to charge and remain constant. As you see, the capacitor is doing what? The voltage across the capacitor, it detects the peak, the maximum of the voltage, of the input voltage. So it reaches to the maximum and stays. When the input voltage increases above this maximum, then the capacitor charges until it reaches the new maximum, and then stays until the input voltage or the source voltage has a higher maximum. Then the capacitor is going to charge until it reaches the new maximum and stays. That's why we call this circuit the peak detector, because it detects the peak of the signal. The capacitor will always charge to the maximum voltage of your signal, right? And it will stay charged with this voltage. That's why we call it the peak detector. This is just a circuit to give you an idea of what happens if we replace the resistor with a capacitor. So the capacitor is going to charge as long as the diode is on. As long as Vs is higher than the voltage of the capacitor, the diode will be on and the capacitor will charge. But if Vs is lower than the voltage of the capacitor, the diode will be off and the capacitor will not charge. Okay? That's why this circuit is called the peak detector. It is used to detect the peak or the maximum value of a certain signal. Now let's go back to the rectifier circuit. What happens if we add the capacitor and the resistor? So if we connect the capacitor and the resistor of course represents our load. What happens if we connect a capacitor parallel with it? Let's see. So this is the second rectifier circuit. It's a half-wave rectifier, but we call it half-wave rectifier with RC load. Half-wave rectifier with RC load. So in this case, we'll assume again for simplicity, we'll start with ideal diode. For simplicity, we'll start with ideal diode. And let's assume that this is our source or secondary voltage. This is the secondary voltage, the voltage at the secondary of the transformer. Okay, it's a sinusoidal wave. What happens is, in the beginning, assume that in the beginning we just turned on the circuit. The positive half cycle, in the positive half cycle, the capacitor is not charged, still the voltage across the capacitor is zero. So in the beginning, in the positive half cycle will allow the diode or will force the diode to be on. So the diode will be on and then the capacitor is going to charge. When the diode is on, in the beginning, in the first quarter half cycle, V input is increasing, so the diode will be on. So here, the diode will be on, and when the diode is on, since we assume it's ideal diode, an ideal diode, it will be a short circuit, okay? The voltage across the capacitor will be exactly the same as the voltage of the secondary, right? So the voltage across the capacitor will be the same exactly as the voltage of the source or the secondary voltage. So the capacitor is going to charge up to here until it reaches the peak. Once it reaches the peak, the secondary voltage or the source voltage is going to decrease lower than the capacitor voltage. So the source voltage is going to decrease lower than the voltage across the capacitor. So the diode will be off because the voltage here is lower than the voltage here. The diode will be off. What happens when the diode is off? when the diode is off, it will be open circuit. And here we have C and R. Okay, this is the output voltage. This is Vs. When the diode is off, what happens is that the capacitor is going to discharge here, right? The capacitor is going to discharge through the load resistor. When the capacitor discharges, the voltage across the capacitor will decrease until it reaches to this point. What happens at this point? What happens at this point is that the secondary voltage is going to be higher than the capacitor voltage again. So the capacitor is going to discharge, the voltage here is going to decrease. At the same time, the voltage of the secondary is increasing again until the voltage of the secondary is higher than the voltage of the capacitor. The diode will be on again. And when the diode is on again, the capacitor is going to charge again, right? Until it reaches here. And then it discharges again. Starting from here, let's assume this is the wave. Starting from here, the voltage of the secondary is lower than the voltage of the capacitor. Then the diode will be off and the capacitor discharges again through the resistor. And this keeps going on and off like this. So the output voltage will look like this. The output voltage will be charging of the capacitor, then discharging, charging, discharging, and so on. Okay? So this is how the output voltage will look like. Charging, and in this part, the diode is on. Then discharging, and in this part, the diode is off. And then charging again, discharging, and so on. And this is the shape of the output voltage in case of RC load. This is the output. The difference between, as you see, the output, it has fluctuations, right? It goes up and down, okay? The difference between the maximum value and the minimum value, we call it the ripple, V ripple. The ripple means the change in the output voltage. We call it V ripple. So the difference between the maximum value and the minimum value is called V ripple. Of course, the maximum value we call the maximum value V output peak. V output peak. Usually V output peak, if you assume ideal diode, V output peak will be equal to Vs peak. But if you assume in general a diode that is not ideal, then V output peak will be equal to Vs peak minus VDO. So V output peak in general is equal to Vs peak minus VDO. Of course, here in this plot we assumed ideal diode. However, if we don't have ideal diode, what happens is that the curve will be a little bit smaller because it will start when Vs is higher than VDO plus the capacitor voltage, right? So in the beginning, capacitor voltage is 0, so it will start when the input is higher than VDO. So the output will start from here, it will reach up to here. This is if we have a constant voltage drop model, okay? And then it will go down up to here, then it will charge again, and then it will go down, and so on. So this is in case of ideal diode. This is in case of constant voltage drop model. The only difference is there will be a difference between the peak here and here by VDO, which is the voltage of the drop across the diode, which is between 0.6 to 0.8. We can assume it's 0.7. So there will be a difference of 0.7 or VDO between the two curves. Okay? So in general, V output peak, the peak of the output is the peak of the source or the secondary voltage minus VDO. Okay? The difference between the maximum and the minimum is called V ripple. So V ripple is the difference between the maximum value of the output and the minimum value of the output. We are interested here to calculate the value of V ripple. We are interested to calculate for how long the diode is going to conduct here, this interval, during this interval, the diode will be on, right? So we are interested to calculate this interval and the value of V ripple, because this is important to know how much will be the change in our output, so that when we design our regulator later, we need to know how much our output is going, the fluctuations in our output is going to be, so we design our regulator to be suitable to this change, right? So what we'll do here is we can mathematically prove it. We can mathematically prove the equations that we are going to see here now. I know that here there is a bit of math here, but I can prove it to you, and I will do a proof maybe of one of them to you. However, I need you to believe me in the rest, and just trust me that these are the correct equations that we should use in order to calculate the conduction interval and of the diode and the rest of the equations. Okay? Of course, if V output is changing, between a maximum value and a minimum value, and the difference between them is V ripple, then it's easy to see that the average value of the output here will be what? It will be V output peak minus V ripple over 2. V output peak minus the difference divided by 2, right? So the average value of the output here is V output peak, the maximum, minus half of this interval, which is V ripple over 2. So this is V output average. So this is one equation that you will see, that the average is V output peak minus V ripple over 2. Okay? And of course, we agreed that V output peak equals the peak of the secondary voltage, or you call it source voltage, minus VDO. So this equation, the average of the output, and this is the relation between V output peak and Vs peak, the peak of the second. What else? We are interested to calculate the ripple voltage. And in order to calculate the ripple voltage, remember that the capacitor discharges, let's focus here for simplicity on the ideal one, okay, ideal case, okay, it doesn't matter. We'll show the equations in general, but let's focus on the ideal case. We know that the capacitor, when the capacitor discharges, what's the equation of discharge? From the transient analysis that you studied before in the circuits course, the capacitor discharges according to an exponential curve. This exponential curve is V output peak, the beginning, the value of the output, the value of the voltage of the capacitor, V output peak here, okay, multiplied by exponential minus T over RC. So the voltage of the capacitor, the output voltage, which is the voltage of the capacitor, here will be V output peak exponential minus T over RC, where R is the resistance of the load, C is the value of the capacitance. Okay, and we need to know that what is the value of V ripple. We know that after some time, let's say this is one period, right? So this is, I'm proving now the equation. You don't have to know the proof, but this is for you just to trust that this is the correct equation. We know that this is a period. This is one period of the sinusoidal wave, and let's call this interval, let's call it delta t. This is the interval where the diode is going to conduct. So the capacitor is going to discharge in an interval that is from here to here. That is t minus delta t. T minus delta t. So we need to know what is the value of the output after an interval t minus delta t. This is the interval where the capacitor is going to discharge, right? We'll do an approximation here. For large values of RC, this coefficient will be very small, exponential minus x. It can be approximated as 1 minus x plus x squared over factorial 2 minus x cubed over factorial 3 and so on. This is the series expansion of the exponential. if x is very small, then you can approximate this as 1 minus x. You can approximate that exponential as 1 minus x. This is what we'll do here. We'll assume that our RC is large enough, okay, to make this factor or this value very small. So we can approximate this. We can approximate this equation to be V of peak 1 minus T over RC. Okay? The value here that we will reach, the value that we will reach after T minus delta T, the value that we will reach after time T minus delta T is what? What's the value here? The value here is V of peak minus V ripple, right? This is V of peak and this is V ripple. So the value that we'll reach here is V of peak, the maximum, minus the ripple. So V of peak minus V ripple is the value of the voltage of the capacitor, at time T minus delta T, which is, this is the voltage of the capacitor at this time. Let's write it like this. Let's write it, the voltage of the capacitor at time equals T minus delta T. Which is what? Which is V of peak 1 minus T minus delta T divided by RC. Here, this is V of peak minus V ripple. V of peak minus V of peak multiplied by T minus delta T over RC equals V of peak minus V ripple. From here you see that V ripple will be equal to what? V ripple will be equal to V of peak T minus delta T over RC. Of course, as you see, delta T, the time that the diode conducts this interval, delta T, usually it's much smaller than the period, So we can approximate this more, we can have a more approximation here by ignoring delta T with respect to T, and we can say that V ripple is approximately V of peak T over RC, where T is the period, V of peak is the peak of the output, R is the resistance of the load, C is the capacitance. Sometimes they write this equation as V of peak over FRC. What is F? F is the frequency, which is 1 over the period. So 1 over the period is the frequency, right? So they can write it as V of peak T over RC or V of peak over FRC. So this is the equation for the ripple voltage. I proved it to you. You don't have to know the proof, but you know that V ripple approximately will be V of peak multiplied by the period of the sinusoidal wave over RC. Okay? Delta T, the conduction interval, of the diode can be also mathematically calculated. You can calculate delta T, for example, by saying, I will give you a hint of how to calculate it without proof, but you can calculate it by saying, if you assume that this is a cosine wave, this is a cosine, let's assume that our zero is here, our zero time is here, okay? Then you say that cosine omega delta T multiplied by V of peak will be equal to, if this is a cosine wave and this is our zero time, imagine that, then cosine omega delta T will be equal to V of peak minus V ripple, and then they approximate the cosine using a series approximation again. They write or they use the approximation that cosine x approximately can be written as 1 minus x squared over 2. Okay? They use this approximation here and they will reach that the conduction interval of the diode, delta T, is 1 over omega, 1 over the angular frequency, square root 2 V ripple over V input peak or V source peak. That's the peak of the source voltage. Okay, this is supposed to be V source peak. Okay. Once you calculated the conduction interval, the conduction angle, if you want it as an angle in radian per second, you multiply delta T, the conduction interval, by omega, you convert it to angle. Omega is radian per second, you multiply by second, you get the conduction angle. Okay? So when you multiply the conduction interval by omega, you get the conduction angle. This is the angle where the diode is going to conduct. The angle, we know that 1 period is equivalent to 2 pi, right? 2 pi, angle 2 pi radian. So here you are calculating the portion of this 2 pi, okay, where the diode is going to conduct. So this is theta. Theta is called the conduction angle. Okay, sure? So this is square root 2 V ripple over V input peak. And V ripple can be calculated from here. V input peak T over RC. So you can calculate V ripple, you can calculate the conduction angle, you can calculate the average of the output, which is V output peak minus V ripple over 2, and you can calculate that the output peak equals the peak of the source voltage minus VDO minus the voltage of the diode. We'll stop this video here and we'll see you in the next video, inshallah.